folks. Everybody got the quiz 3 up here? None accepted after this time. Let's get on with electrochem. We're still looking at question 2215 in regard to developing equations for half reactions, which of course involves learning the rules for such, and then coupling the half reactions to get net cell reactions. Again, some of you have seen this, most of you have seen this, but to be sure everybody sees it. We'll proceed from part 8 of question 2215. The material which is being oxidized as well as being reduced is cuprous oxide, copper 1 oxide, this stuff. Electrochemists often call a reaction like this as Otto redox. Otto redox is just a fancy word which means for the redox reaction in question, the substance which is being oxidized is also the substance which is being reduced, like this case for cuprous oxide. To consume the oxide ion component, hydronium ions, this is done in 1 molar sulfuric acid solution, or 2 molar, whatever the notes say. And the oxidation product is hydrated copper ion. So you need the requisite number of water molecules in addition to those which are produced by deprotonating the 2 hydronium ions. And when the 2 H pluses land on oxide, you make the remaining 12th water to give you the required 12 total moles of water to make 2 total moles of hydrated copper ion. The reduction part is the conversion of cuprous oxide to copper metal. Same chemistry regarding consumption of oxide ion as it puts it in solution. So water molecules, again, the product. 2 electrons produced, 2 electrons required, add them up, ready to go. For a system like this, what would you say regarding system pH as the reaction runs? pH go up, come down, stay the same. What would you say for this system?
Go up.
pH is going up. Why?
Because there's no strong acid left at the end of it.
Well, don't say what isn't there. Say what happens. What's happening?
All the hydroxide went away?
Well, what hydroxide? There's no hydroxide in this.
Hydronium.
Hydronium ions are being consumed on a net consumption basis. Not surprising, since the hydronium ions are reacting with the oxide ion component of cuprous oxide as a reactant in each half reaction. 9, for the half reaction corresponding to oxidation, it's the same as what we have up there. In this system, cuprous oxide is being oxidized by hydronium ion. So there's the half reaction which we looked at, for example, in doing our redox demonstration the other day. 10, potassium with water, that's the same as sodium with water. How does the reducing capacity, capability, strength of elemental potassium compare to elemental sodium? Which is a stronger reducer?
Potassium.
On what basis do you say that? Your statement is correct. I don't care about votes. Why is your statement correct?
I'm not explaining.
Anybody? Why can we gather that potassium is a stronger reducer than sodium? What do you think reducing strength has got to depend on? Does not the ability of any of the 1A metals to behave as a reducer involve 1 electron loss per atom? Right? What's the change in energy associated with electron loss? You did this in 2045, put it to use. What's it called? An atom loses an electron, becomes a positive ion. What's change in energy for that process? Change in energy. Don't remember? Ionization energy. You created an ion, didn't you? Now you got to be careful about terms like this. Because if an atom collects an electron and becomes a negative ion, you're also creating an ion. But the change in energy for that process, when an atom collects an electron and becomes a negative ion, what's that change in energy called? What's it called? You did this in 2045. It's called electron affinity. Because that change in energy is a measure of what affinity the atom in question has for electrons. So, which has the lower first ionization energy, K or Na? K must, because it's the better reducer, with no other factors being considered. Why should K have the lower first ionization energy? It's a larger atom. You remember recognizing that in the nucleus of potassium you got 19 protons, nucleus of sodium only 11 protons. Yet sodium is harder to ionize. So clearly, the net nuclear attraction for valence electron K, even though it's got many more protons, has got to be smaller than the net nuclear attraction for the valence electron of Na. Why is that? Because Na is a good deal smaller. Because what matters most is how close those electrons are to the nucleus. Ain't that right, Coulomb? Remember what Coulomb's law says? Q1 times Q2 divided by D squared. What's that D squared term?
Distance.
D is distance between what? Distance between what? The electron and the protons in the nucleus. Or the electron in the nucleus, who cares? The valence electron in the nucleus. And in the denominator of Coulomb's law, that D term is squared. Which means as you move further from the nucleus, the attraction force falls off by a square factor. Which is why the larger atom will have the lower first ionization energy or subsequent ionization energy requirement compared to the smaller atom. It's again the case of zinc being oxidized in hydronium ion, where you get hydrated zinc ion and hydrogen gas as products. 12, we did this by demonstration, copper oxidized in nitric acid solution, where you get hydrated copper ion and as the principal redox product, NO gas. In addition to hydrated copper ion. Now, car battery chemistry. How many of you are an owner of this chemistry? That's all? Everybody else is going by bicycle? Or is it private jet plane? I don't know. Is it underground railway? I don't know. Is it by foot? Okay. Chemically, the car battery is very simple. Only 3 components. Lead metal, lead dioxide, which contains lead in what oxidation state? Oxidation state of lead and lead dioxide. +4. And 4.5 molar sulfuric acid solution, for which the principal species inventory is hydronium ion, AQ, what else? Hydrogen sulfate ion, AQ, and water. Bingo. So, now we'll squeeze it in there. If you are told that the half reaction occurring at the anode and the half reaction occurring at the cathode each produce lead sulfate, you have now enough information to develop the correct half reaction equations, which can then be coupled to get the correct net cell reaction for the chemistry that occurs in the car storage battery, your lead battery in your car. Okay? So I'm taking the liberty of going straight to each half reaction. Now we'll talk about them. If lead is being oxidized in the anode half cell, because the anode half cell is the half cell in which oxidation occurs, to lead sulfate, then hydrogen sulfate ion's got to be a reactant, because it's your main sulfate ion source in this system. And when hydrogen sulfate ion is stripped of H+, to provide sulfate ion to make this stuff, where's the H+ land? I don't want a specific species answer. I want the answer that's always right. Strongest base present in appreciable amount or concentration in the system. Well, there's our PSI. So water wins this time. Cathode. Lead sulfate is again a product. Well, the only lead-containing stuff that could possibly be reduced to lead sulfate is lead dioxide, where lead is starting out in the +4 oxidation state and winding up in the +2 oxidation state. So I've got to murder 2 oxide ions in this process. They're liberated to the system as lead dioxide is converted to lead sulfate. And again, I need my sulfate source. Well, to murder these two -2 oxidation state oxygens, these 2 oxide ions, what will the murderer be? The strongest acid in the system in appreciable amount or concentration. And for the most part in this system, that's hydronium ion, because that's a stronger acid than hydrogen sulfate ion. But remember, the strongest Bronsted acid, period, is what? What is the number 1 strongest Bronsted acid? Nothing can be stronger than this Bronsted acid. What is it? What is it? The strongest possible Bronsted acid. You got it. Which has got a Ka value of infinity. How about that for strength? That's why you're not going to have any H pluses floating around free in any system. And 1 H plus is given to the system by doing what in this half cell reaction? Where does this 1 H plus come from? Does it come from deprotonating this to make sulfate ion? Huh? You betcha. So I need 3 additional hydronium ions to give me my 4 total H pluses, which I need to murder my 2 oxide ions and turn them into water molecules. Okay? So here I'm totally protonating 2 oxide ions, that makes 2 waters, and deprotonating 3 hydronium ions, that makes 3 more waters. That's where I get the 5 waters. All right? So those are the electrochemical potentials. Now before we go forward to this, I'll ask this question. From this information, the anode half cell reaction, the cathode half cell reaction, can you answer the question, which is more thermodynamically stable, lead or lead dioxide? Notice that in this system, each of these materials has a reactant, lead and lead dioxide. They each convert to the same product, don't they? So the difference in thermodynamic stabilities is not going to have anything to do with the product, since they each convert to the same product. So I repeat the question. Which material, lead or lead dioxide, is the more thermodynamically stable stuff?
Lead dioxide.
I heard a vote for lead dioxide. Okay. Tell me, any of you people ever go fishing? Anybody go fishing? Or is everybody spending all their life outside of class, sitting in front of that damn computer, playing games? Like bong pong or whatever the hell these things are, I don't know. Smashing fruit, no, who knows what, I don't know. I don't bother with any of that stuff. It bores me to tears. The only game pleasure I've ever derived from a computer is finding a computer not a computer, but a program which offers chess playing at grandmaster strength, and that's what I play, because that's fun. And in 1963, because in undergraduate school, my main passion was not being a student, I will admit. My main passion was playing chess. And in 1963, the United States, it was 63 or 64, I can't remember the year for sure. The United States Intercollegiate Chess Team, comprised of the best 4 U.S. college players at that time, were the only U.S. Intercollegiate Chess Team to win the International College Chess Competition. Why did they win? Because that year the competition was played in Israel and the Soviets refused to send a team. Because if the Soviets send a team, the Soviets win. Because they were all strong grandmasters. On our team we had no grandmasters. We had 4 senior masters. That's not bad. Of those 4 senior masters who captured the U.S. Intercollegiate Chess Championship for the one and only time, I played every one of them in tournaments before they had that. And I beat 3 and drew 1. Not too bad for an average chess hacker. Them days I was pretty good. Now I'm still pretty good, but it takes me a hell of a lot longer to figure stuff out, because the brain just doesn't work as fast. Well, in any case, let's get away from that kick and go back to this. Lead or lead dioxide? Lead is more thermodynamically stable, but I want to hear a vote for lead dioxide. All right, time for a vote. Lead is more thermodynamically stable. How many vote for that? Lead dioxide, how many vote for that? Now then, what information do we have here to allow us to answer the question? What? The E-naught half cells, right? Which one shows by far the greater tendency to proceed as written? This one, doesn't it? Right? That's plus 1.68 volts. The other one is 0.36 volts. Which means this has a far greater tendency to consume electrons and convert to lead sulfate than this does to lose electrons and become lead sulfate. So this is the more thermodynamically stable. You think I might ask questions like this on the last exam? Because I want you to understand this stuff. That's where the fun is. All right, now a comment. Take a look, please, if you've not yet done so, at page 2218 in the notes, where there's a caption at the top of this page, writing net cell reactions. Because I've got a goof in this part of the notes, and I want to try to untangle this goof right now. When I recognized that it was necessary to consider the possibility of separating the anode half-cell system from the cathode half-cell system to avoid creating a short circuit to make an electrochemical system which can deliver usable electrical energy? I thought that applied to every electrochemical system that was to be serving the purpose of behaving as a battery, a voltaic cell. Well, I was wrong. So, finally, after having a chance to think a little bit further about this, I recognized that what you have to have in order to be able to have an electrochemical system that gives you usable electrical energy, doesn't have a short circuit, is to be sure that even though all the material components may be in the same system, there's no separation of the half-cell components, oxidation half-cell components, reduction half-cell components. As long as the reducer itself is physically separated from the oxidizer itself, you're okay. And if you take a look, for example, with Google, at a diagram of the lead storage battery. What you do, put lead storage battery, Google, boom, out comes a picture. And it'll show you just how the thing is constructed. There's nothing wrong with having lead and lead dioxide in the same system without any half-cell separation, because these are the half-cell reactions. All you got to do is be sure this stuff doesn't touch this stuff. And then you don't have a short circuit. That's easy to achieve, don't you see? Because these are each solid phase. So put the lead over here, the lead dioxide over there. Who cares? As long as they're not touching each other, they don't have a short circuit. Okay? That means when I develop the net reaction for this system, and I see 3 hydronium ions as reactants and 1 hydronium ion as a product, I don't have to keep these separated, because they're not part of the redox chemistry of the system. They're part of the chemistry of the system, but not part of the redox chemistry of the system. So I can take this, call it 2, and take this out. Okay? Nor do I have to keep the hydrogen sulfate ions separated. Like plus hydrogen sulfate ion, plus hydrogen sulfate ion. I thought that was necessary when I first did this. I said, wait a minute, these are not in touch with each other. I don't need to keep these apart. Who cares? They're swimming around in solution. Who cares if they touch each other? So, 2 hydrogen sulfate ions rather than hydrogen sulfate ion plus hydrogen sulfate ion. Now, look at the cell reaction that's written on page 2218. It's near the top. It shows the oxidation of zinc by reducing ferric hydroxide in the presence of hydroxide ion, with the reduction product being iron solid and zinc hydroxide gel. Okay? Is there any need for that electrochemical system to function properly to keep the half-cell systems totally separated? No. All I got to do is make sure the zinc doesn't touch the lead hydroxide. I mean the iron hydroxide. That's all. Same idea as here. Okay? Now then, what about this system? Because we did this system as a demonstration. And when I did this system as a demonstration, I showed you what happens if we put the zinc, which is the reducer in this system, in contact, direct contact with hydrated copper ion, which is a solution species in this system. Remember that? Then immediately, copper ions convert to copper metal and lay down on the surface of the zinc. That's a direct electron flow, a short circuit. So here I got to have separation. Physical separation of the half-cell components. Because if I don't physically separate these half-cell components, I'll have the zinc in contact with this. If these are all in the same solution, how can I put a zinc bar in there without touching this? And as soon as the zinc bar touches this, boom, short circuit, all done. So here I got to have physical separation. So to decide when or when not physical separation is required to have an operating voltaic cell, a battery, requires that you examine the system and pay attention to the system components and make a decision accordingly. In the coming conversation, we'll take a look at another case where I'll ask you to make a decision in a few minutes. All right, 2217. I don't want to rewrite the questions on the board. 2217 says, based on information which can be taken from our redox demonstration or from the information which we've just finished considering as part of question 2215. Okay? How can we say for sure that zinc is a decidedly poorer reducer than potassium? If Joe is taller than Sam and Sam is taller than Mo, then how do the relative heights of Joe and Mo compare? Joe taller than Sam, Sam taller than Mo. So, how does the height of Joe compare to Mo? Joe's got to be taller, right? Didn't we a moment ago argue that potassium is a stronger reducer than sodium? Okay. And what does sodium do in touch with water? Kaboom! What does zinc do in touch with water? Nothing. Well, potassium is one heck of a lot better reducer than zinc, because it's a better reducer than sodium, and sodium has already been established to be a far better reducer than zinc by the fact that sodium beats the living hell out of water in contact with such, and zinc, practically speaking, does nothing. All right? B, hydronium ion is a stronger oxidizer than nitrate ion. Now tell me, as a consequence of our redox demonstration, where, as part of that demonstration, we found that zinc is readily oxidized in, say, 1 molar sulfuric acid solution, where we recognize that hydronium ion is the oxidizer. Okay, so far? This we did. If you didn't know about the relative oxidizing strengths of hydronium ion versus nitrate ion, as oxidizers, what experiment would you do to find out, or what experiment could you do which perhaps, I should say, which perhaps would let you find out? If you know that zinc readily oxidized in 1 molar sulfuric acid solution, which allowed us to decide that zinc in this system is being oxidized by hydronium ion. You remember what we did with copper? Copper in 6 molar nitric acid solution, away it went. Copper in 9 molar sulfuric acid solution, nothing. And we recognize that copper in the 6 molar nitric acid solution involved reduction of what? What got reduced? When copper was oxidized in the 6 molar nitric acid solution, what got reduced? Nitrate. Nitrate ion. You got to reduce to NO. Remember that? So we asked the question, is concentrated nitrate ion by itself capable of oxidizing copper? And what experiment did we do to resolve that? We put a copper strip in 6 molar sodium nitrate solution, because 6 molar sodium nitrate solution has the same nitrate ion molarity as 6 molar nitric acid solution, doesn't it? What did the copper do while standing in the 6 molar sodium nitrate solution? Not a thing. It stood there peacefully without reaction whatsoever. So that told us that for nitrate ion to behave as an oxidizer of copper, it needed the support of hydronium ion. It needed the support of an acidic system. And the simplest way to make a system acidic with water being solid is to enrich the system in hydronium ion. So if we're in the lab, we do an experiment, we put a zinc strip in 1 molar sulfuric acid solution, which we already did, and we see ready oxidation of zinc as hydronium ion is reduced to hydrogen. What experiment might you do with the zinc to resolve this issue? Hydronium ion versus nitrate ion individually, relative oxidizer strength being the question. What experiment might you do? Because with this we find that hydronium ion oxidizes zinc. What would you do? I'll give you a hint. First I'm going to give you a strip of zinc. Okay? Then I'm going to send you to the side shelf and invite you to select a particular solution. What solution might you select?
Sodium nitrate.
How about sodium nitrate solution? 1 molar. 6 molar. You put the zinc in there. Reaction? None. 0. So, if zinc is readily oxidized by hydronium ion, but zinc is not oxidized by nitrate ion, with the nitrate ion being at the same or higher molarity than the hydronium ion, this has got to be the stronger oxidizer. Done. And then lastly, silver cannot be oxidized by 1 molar hydronium ion since silver cannot spontaneously reduce hydrated copper ion. What we want you to do is to put puzzle parts together in behaving like Sherlock Holmes. Make educated decisions as best and as well as you can from the information provided, the information you have available. Okay? So we're being told this is a no reaction system. You could also make that decision by looking at the half reactions in our table 2 in chapter 22. Okay? So, any reaction here? Or is it the case that as yet you cannot decide? And that ain't the case. You remember the investigations we performed to try to see about getting copper to be oxidized? Did copper do anything in 1 molar sulfuric acid solution? Nothing. Did copper do anything in 12 molar sulfuric acid solution? Well, we tried 9 molar. 9 molar. Copper do anything in 9 molar sulfuric acid solution? Nothing. So hydronium ion is not capable of oxidizing copper. So the question is, how about hydronium ion being capable of oxidizing silver? Well, if silver can't reduce this, then tell me, how does the reducer strength of this compare to this? What would happen if I take copper and put it in contact with silver ion aqueous? Because as far as reducers go, these two, one of these has got to be stronger. There can't be any other way. And if this cannot reduce the conjugate oxidizer of this, then it must be true that this can reduce the conjugate oxidizer of this. Because what we've concluded, if this can't reduce this, this has got to be a stronger reducer than this. And this can't be oxidized by hydronium ion. All the way up to 9 molar, we tried it. So you can oxidize this with this? Never. Enough said. All right, we did this. And now we go to electrochemical arithmetic. 2 principal parts to electrochemical arithmetic. Faraday's law and the Nernst equation. We start with Faraday's law. Just for the sake of clarity and communication, we'll repeat some of the information that you see in the notes regarding Faraday's law. J joule, energy unit, is identical to energy unit volts, a measure of potential, times electric charge unit, Coulomb. Symbol cap C. All right? And Coulomb is equal to identical to volts. No. Wait. Get this out of here. Capital A times time expressed in seconds. That's what small s is, second. What's capital A? What is it? Amperes or amperage. What's that? Unit of what? Current. That's charge flow per unit time. So charge per time multiplied by time gives us charge. Coulomb. Nothing fancy about this. Okay. Now then. And the Faraday itself, which is defined as 1 mole of unit charge. In other words, the Faraday is by definition the total electric charge borne by a mole of electrons. And that is given by 1.6 times 10 to the minus 19 coulombs per electron. Did you talk in 2045 about how that value was determined? Nobel Prize winning experiment by Robert Mulliken, University of Chicago, 1908. Did you talk about that? The famous oil drop experiment? Didn't talk about that? Did or did not? Don't remember? Too far along? Ancient history? Can't possibly remember anything past yesterday? Okay. Maybe even a couple hours ago, I don't know. Times the number of electrons in a mole of electrons. Well, the number of particles in a mole of particles is that number. And in this case, the particles are electrons. When you grind this out, you get to 3 sig figs 9.65 times 10 to the minus 4. I mean 10 to the 4th, pardon me, coulombs per mole of electron. That's all you need to get at Faraday's law. So here's Faraday's law. Written as an equation. It's usually written this way. M, which represent mass, in this case mass of reduced or deposited material. Material deposited as a consequence of chemical reduction. Like putting chrome metal on an automobile bumper. Well, I don't think they make metal bumpers anymore, but they did back in my day. They used to take the bumper and immerse it in a bath containing chromium ion and reduce the chromium ion by turning the bumper into a cathode. Then the chromium ion would travel to the bumper and deposit as chromium metal. Chrome plating bumpers. Q. This is not squiggly Q. This is not reaction quotient. This, unfortunately, is representing what in this expression? Do you know? Charge in coulombs. Sometimes we run into headaches like this, like K for equilibrium constant, K for temperature Kelvin, stuff like that. And this is my not too good sketch of fancy squiggly M, which represents formula mass, divided by the Faraday dot N. Well, we got the Faraday up there. What's N? Moles of what? Moles of electrons transferred for the redox reaction to which Faraday's equation is being applied. So how am I going to get N? I have to look at the equation for the reaction. That's the only way to get in. Okay? So just to be sure, we'll write this over here. Charge in units of coulombs. Okay. M is formula mass. F Faraday. N moles, electrons transferred or required, whatever. And M is mass of material produced by reduction, which we abbreviated with R in parenth. Okay. Now, oftentimes the mass of the material oftentimes the material produces a metal, but it doesn't have to be. Anything you produce by reduction is determinable what this. So is determinable arithmetically, the amount thereof, by this relationship. So in sum, what Faraday's law applies to is running a spontaneous redox reaction in the opposite direction. Do you have a device in your automobile which serves this purpose? What is that device?
Alternator.
Alternator or generator, either one. What does the alternator or generator do? Or is it just some mystical black box you have under the hood of your car? You don't know what the hell it is, but you'll know if it doesn't work, you got a problem.
Keeps the battery charged.
Keeps the battery charged. It runs the battery reaction in the opposite direction. And we had, whoop, I took it off. We had the battery reaction up there a moment ago. It reconverts lead sulfate to lead at the cathode when you're running in reverse, and lead sulfate to lead dioxide at the anode when you're running in reverse. The reverse meaning the reaction which is given by the lead storage battery when it operates spontaneously on its own. You want that to behave anti-spontaneously. Here's what you consider. And your alternator generator serves that purpose. Okay, now then, in the notes, you'll see some questions and answers that are discussed to assist your ability to understand use and application of Faraday's law from a practical standpoint. The notes discuss First, running an electric current through silver nitrate solution. We electrolyze silver ion and reduce silver ion at the cathode to make silver metal, for which we wrote the half reaction at the bottom of page 2219. And some arithmetic that follows from Faraday's law considerations at the top of page 2220 to show you ultimately what mass of silver will be produced by the electrolysis process which has been defined. And then we go to another question, which involves the oxidation of zinc. A battery is now delivering a 1 amp current as a consequence of zinc being oxidized. We don't care what's oxidizing the zinc, but zinc is a common reducer in many batteries, cheap, inexpensive batteries, because zinc itself is not very expensive. As I believe we mentioned before, for example, today pennies are, practically speaking, almost all zinc rather than copper, because the copper is a whole lot more costly, more expensive, okay? So for this issue, how long does the battery operate? Now then, with these units related to the problem, which of these puzzle parts do you think you have to pay attention to if you're doing a Faraday's law calculation and want to get how long? You want to get time. Well, which one of these units contains time as a component? Coulombs, isn't it? Because coulombs is amp second. Well, that means you're going to use this Faraday, because this is amp second up here, so you can get a handle on time. Then we've stated if this battery is manufactured from 2.50 grams of zinc, and the only positive oxidation state developed by zinc in its chemistry is +2, which we presume you know at this stage of the game. Then we've done a calculation to show that this battery will deliver the indicated current being 1 amp for 193,000 seconds. And if you convert that to hours, you get 2.05 hours. So what? Now then, let's go to 2218. For battery described how much aluminum required to make same battery. A battery which is going to give us the 1 amp current, battery which is going to last for 193,000 seconds. First question, to wrestle with this, or first consideration to wrestle with this. Do we have to apply Faraday's law? Directive. Any of these Faraday's law computations, or any computations related to Faraday's law, demand that you pay rigorous attention to unit or as it's also known, dimensional analysis. You got to let the units talk to you. That's the way to do it. All the time. In fact, when you do any calculation involving measured data, which of course we're doing all the time in physics class and chemistry class and what have you, unit analysis is the only way to proceed. Because when you create a setup for doing some arithmetic to answer the numerical part of a question, if the setup you've written does not generate the correct unit or units, the unit or units that the statement of the question or problem call for, I don't care what you do with the numbers, the calculation with the numbers will be meaningless because it's not giving you the right unit or units. Fair enough? So this says, I want to make the same battery, only instead of using zinc, I want to use aluminum. Well, we have recognized that the battery in question was fabricated with how much zinc? How much zinc? 2.50 grams? And when we deal with quantities in chemistry, the fundamental quantity with which we deal more often than anything else is called what? It's called a mole, isn't it? Can I figure out how many moles of zinc I got here? If for a pure substance, in this case zinc, I have a measured sample whose mass is known, and I want to know how many moles of the stuff I got, what am I going to do? What property of the stuff always allows me to relate its mass to moles or moles to mass? Formula mass. Bingo. So I get out my periodic table and I see for zinc 65.4 grams per mole. Let me check my data because this thing doesn't have formula masses. Yeah, that's right. Okay. Now, from an electrochemical standpoint, what difference do I observe when in one case zinc is functioning as a reducer and becoming oxidized, and in the other case aluminum is functioning as a reducer and becoming oxidized? What's the principal difference between these two materials? Because we're talking about liberating electrons, right? From a mole of zinc as it is oxidized, how many moles of electrons are liberated? Two. But when a mole of aluminum is oxidized, how many moles of electrons are liberated? Three. And therein lies the rub of the grin. Therein lies what I need to know to write my ever so simple setup to solve this puzzle. I want to know moles of aluminum, right? Just how much aluminum do I need? And if I want to convert it to mass of aluminum, I can do that. So when I now write my setup to answer this simple question, what should I write first? What's the first factor I should write down to create this setup? I'm listening. Nope. That's a textbook way. We're not doing it that way. That's a bad way. What did this question ask you to get? Did it not ask you to get moles of aluminum? That's what it's asking you to get. So the first thing I want to write down is a factor which relates to moles of aluminum, because that's what I want to get. So whatever this unit or units, this question as it is stated or problem as it is stated, tells me to get, that's the factor I'm writing first. And if I do that, I can't go wrong with a dimensional analysis. I mean it, the textbooks are back-asswards on this stuff. They got it wrong. Because if you do it the textbook way, and I give you a whole pile of units to fight through this, you're going to have a real headache. But if you let that question talk to you, it says, look, these are the units I got to get. So I write down first 1 mole Al. In this case, 1 mole of Al per what? What is the electrochemical connection between oxidizing aluminum and zinc? We just talked about it. When zinc oxidizes, how many moles of electrons? 2. When aluminum oxidizes, 3. So I want to write 1 mole of aluminum per 3 moles of electrons. Now, I don't know any recipe or formula to write down. This comes from dimensional analysis. We're letting the question talk to us, okay? Well, ultimately, as an answer, I want moles of aluminum and nothing else. So when I'm going to write my next factor, I will purposely write my next factor containing units which will do what to this? Cancel it, right? Because I don't want this in the end. All I want this is, in the end, is moles of aluminum. And what can I write then next? 2 moles of aluminum. 2 moles electrons per mole zinc. You got it. And there that goes. Boom. There goes moles of electrons. So I know I'm on the right track. So now I got to eliminate moles of zinc. But the reference I have to quantity of zinc used for fabrication of this battery is the 2.50 gram. So what should I write next? Well, I want to get rid of this unit now, don't I? Just let this thing talk to me. Mole Zn per what? Formula mass. And there goes moles of zinc. And when you do dimensional analysis in this fashion, you will realize, what the heck did I do with, there it is, okay. That the last factor you will write down to complete construction of your setup is always the factor upon which the calculation depends or is based. That's what the textbooks start with first. I don't like that, because I know if I start with this, I gotta be on the right track, because it says I gotta get moles of aluminum. So I'm gonna write that down first. How can I be wrong? But this is the mass quantity of zinc that I have to relate ultimately to the aluminum. And now I'm not going to do any arithmetic other than look at what happens when I do the indicated multiplication on the units. What's left? Moles of aluminum. Got to be right. It can't be wrong. And now I'll get out my push-button calculator and do the grinding. At this point, who cares what the answer is? Well, unfortunately, with this multiple choice crap junk that you have to deal with, you have to care what the answer is. But if you're taking a real exam and you write this down, the question's worth 10 points. You got 9 at least. You've told me you know how to do it. That's what I want to know. But if you bubble in the wrong circle, the blind, dumb machine, all it sees is a wrong bubble circle. You go, bee, you get nothing. That's no way to run this place. Okay. We'll write it down in case you want. Okay? Now then, next part. Or next question, I should say. 19. 19 is asking about the electrolysis. We're going to run an electric current through a system. What's the system? Molten MCl3, a metal chloride. And this have you seen this symbol before? I'm just curious. Maybe you've seen it in physics class someplace. This is a symbolic indicator of electrolysis. That means electrolysis. Okay? So I'm going to consider electrolysis of, or electrolyzing, MCl3. Okay? And in this process, I will get, after I carry the electrolysis out for the indicated period of time with the indicated current. This is all there. The indicated current is 10 amps. The electrolysis run for 25 minutes. That's all in the statement of the question in the notes. I wound up producing, at which electrode, 2.695 grams of M, the metal. Okay. At which electrode am I making the metal? What's the electrode at which reduction occurs? Huh? Cathode. Okay. For this electrolysis system, what am I making at the anode?
Metal solid.
What happens at the anode? What happens electrochemically speaking at the anode? Oxidation, doesn't it? Well, if for this system, M3 plus whatever M is getting reduced, then what's got to get oxidized at the anode? Chloride ion. That's all you got there. So if I oxidize chloride ion, what am I making at the anode? Would it be a material you'd like to take a nice deep breath thereof? Chlorine gas is what you're making at the anode. It's important stuff commercially. But when you deal with a problem like this, hey, look at it from all angles. But in this case, we're concerned not about the amount of chlorine we will produce. We could decide that after we answer this question. Or don't even have to answer this question, answer the question how much chlorine is produced at the anode. We want to know by production of this quantity of this metal by this electrolysis process, with the indicated current of 10 amps being run for 25 minutes. Okay? What is the metal? Well, it's got to be one of these things. Unless you're on some planet that I don't know about. Planet Og or someplace, where they got mythical elements, or elements that we don't know about. Okay? Is that where you're at? On planet Og, where you got the famous elements Gazuk and mud. I must say Gazuk and mud, because when stories about planet Og were told me when I sat as a teaching assistant my first year at the University of Florida in 1967, the lecturer, who was marvelous at this stuff, talked about the mythical elements Gazuk and mud on planet Og. Far be it for me to change that. I mean, that has to be preserved. That's a historical fact. On planet Og, there's the elements Gazuk and mud. And that's with 2 D's on mud. Like Roger. Mud. Newsman. Never mind. We want to find out what this metal is. What property of this metal must we calculate to find out what it is? What is it? Formula mass. We got the mass. We want formula mass. Thus, must calc FM, formula mass. All right? So we're now going to write a setup. What should we write first? We want to get formula mass of the metal, don't we? What should we write first? Current, time, Faraday's factor. What the heck does this question demand we get? Formula mass of the metal. Unit analysis in action. And what are the units on formula mass? Grams per mole. How about that? So in the numerator I want grams. So the first thing I'm writing down is 2.695 grams metal. Right? Isn't that the mass of the metal I'm dealing with? Good. Now then, to get the units for formula mass, I want mass of the metal per mole of the metal. What factor can I now write based on the information given that will place in the denominator moles of metal? You've got to do dimensional analysis with this. The hell with recipes. Because with the dimensional analysis application done correctly, you understand, and that's what we want. You'll always be successful if you understand. But for this particular stuff, this system, what factor can I now write which will place in the denominator moles of metal?
3 moles electrons per mole.
Yeah. Doesn't this formula tell me that if I want to clobber this metal and turn it into elemental stuff, that its oxidation state is +3? Because the chloride ions reach -1? Which means to make a mole of this metal, per mole of metal made, I got to add how many moles of electrons? 3. Goody. So I'm going to write 3 moles of electrons per mole of metal. And now we're on our way, because here I got mass of the metal, here I got mole of the metal. So if I just continue my setup construction, so all the units go away except this and this, I got it made. So what do I got to eliminate now? Moles of electrons, right? Or what can I put in here that will eliminate moles of electrons and allow me to factor in the other quantities upon which this calculation must depend. I mean depend, not defend, depend. Okay? Because I read the question, it says I'm running a 10 amp current, I'm running it for 25 minutes, blah, blah. But now my unit dimensional analysis has given me mass of the metal, per mole of the metal, but up top I got moles of electrons. What can I put in here now to get rid of moles of electrons? The Faraday. So do I want the Faraday as written, or do I want the Faraday inverted? 96,500 coulombs per mole of electrons, right? Goody. And a coulomb is an amp second, so I'll write that straight away. And there goes moles of electrons. Now what do I have to get rid of? Amps and seconds, don't I? Now I'm running this system with a 10 amp current. So do I multiply by the 10 amp current or divide by the 10 amp current? You want to wind up with amps squared, whatever the hell that means? So there goes amps. Now I got to get rid of time, don't I? So do I want to multiply by time or divide by time? Divide by time. And what's the time? 25 minutes. So I'll write 25.0 minutes. But now I still have one remaining minor unit headache, don't I? Because this is in seconds and this is in minutes. So I now have to go in my Google, because I don't know how many seconds there are in a minute, because I come from OG. And on OG we don't use minutes. We use squiggle blooms. Right? And we don't have wristwatches. We have Humbaha's. You go to the Humbaha store and buy a Humbaha, you put that on your wrist. And there's 92 Humbahas per Hubaha. or whatever the hell that is. And that's all there is to it. There's the seconds gone and the minutes gone, and if I now do the calculation based on the units, I got moles of metal, grams of metal per moles of metal. I gotta be right, I can't be wrong. And here's what you're gonna get. The 3 sig fix 52.0 grams per mole. There's a periodic table which got formula mass information in the notes. Tell me what the metal is. Or in the information sheet. What is it? Chromium. All right. We'll pick it up from this point next time. And I expect next time to finish electrical